Hello, my mathematically minded friends. We have seen in the last video that root 2 is an irrational number. Root 2 is not in Q, and I will leave a link to that video in the description box. But we can go further than this. Why stop here? There's more that we can get out of this. If we examine this further with different tools, we can prove something interesting. And what we're interested in proving are some peculiarities about the set of rational numbers. These peculiarities shed some light about why we don't just use rational numbers for everything in mathematics and why mathematicians had to introduce R, the real numbers. So let's get to work on that. Let us define two sets A and B in the following way. I divide up my real line like this. Everything before root 2 is here on the left, and everything after root 2 is on the right. And I define set A to be like this. All the rational numbers x such that x squared is less than 2. So these are all in Q. They're not real numbers. It's with the benefit of hindsight that I know I can call this root 2. But right now we actually don't know what root 2 is. Let's pretend we don't know what it is, because let's pretend all we know are the rational numbers Q, and root 2 is not one of them. Now, the set B, I can likewise define it as all numbers above root 2 or such that x squared is greater than 2 with x in Q. Now, the way I have defined these set A and B does not do anything about irrational numbers. You see, x squared greater than 2, everything is rationally defined. Okay, so this, again, let me stress that this is just with the benefit of hindsight to make things a little bit more easy to imagine. So A and B, they're both subsets of the rational numbers, and they are both defined in terms of the rational numbers Q only. Now let's think about this a bit. If I have two rational numbers here, x1 and x2, let's say, I can always make some rational in the middle. And so intuitively, I feel that there's an infinite number of rationals in A and an infinite number of rationals in B. So let me write down what intuition tells me. Well, I have an infinite number of rationals in A and B. I can guess that. And also, I think, if I have a rational in B and a rational here in A like this, I can probably make one that's closer to root 2. So, intuitively I can say I can get as close as I like to root 2 with rational numbers. Of course, I can't get exactly root 2 because we proved that this is impossible. So this is intuitive, but it's of course not sufficient. We have to prove things. This is just intuition. And so we will prove some aspects of this. Yeah, we will prove some aspects of this intuitive picture. And the tool that we're going to use to study this is called the Secant Method. And I'm going to talk about the Secant Method now. The Secant Method is a very useful technique for obtaining rational approximations to roots. So suppose I want to find the root of f of x. In other words, when is f of x equals to 0? And I want to approximate this x. This x might be irrational, but I want either like a numerical approximation or a rational one. Well, use the secant method. That's one way. There are many other ways, but secant method is pretty good. And it works like this. So I have my curve here, f of x. And I'm looking for the root. The root is where this curve intersects the x-axis. So I start off with two guesses here, this one and this one. So I have x0 and x1. These are initial guesses. I need two of them. And you'll see why. Because with these two, I can create now here x1 y1 and x0, y0, I can have now 2 points on this line, 2 points on this curve, and draw a line through them. This is my secant line, and I get this red dot here, x2. So the red dot x2 is my new or better approximation to the root. Okay, so let's compute x2. How do we compute x2? Well, from the guess x0 and x1, I have these 2 points here. I have, let me write that down. I have those 2 points, and I can use the 2-point line formula. And it looks like this. Y minus y1. Choose one of them, so I'll choose x1, y1. X minus x1 equals the slope y1 minus y0 over x1 minus x0. Okay, now use the curve y is f of x. So y1 is f of x1, and y0, that's f of x0. Okay, so yeah, we go up here like this to find the y coordinates of these points. So I take this and I plug this into my 2-point line formula, and what do I get? Well, I just substitute these things here, and I get this formula here. I didn't do anything clever, just put those values in. And now I can get my line in the form y equals mx plus b. Just for fun, let's do that. I just solve for y. And there you go. That's the slope-intercept form. Well, I put the intercept first. Okay, so now we are trying to find that red dot, yes? Where's the red dot? Here. All right, so how do we find this red dot? Well, we know the equation of this line. We have it right here. And how do we find the red dot? Well, the red dot is when y equals 0, because y equals 0 on the x-axis. So now I plug in y equals 0, y equals 0, and what do we get? Let's see what we get. Bit of algebra, and I'm going to solve for x because I want to find x2 here. I want to find the x coordinate of the red dot. And there it is. I did a little bit of algebra and I solved for x. So as an exercise, do the algebra yourself. It's very easy and fun to do. Okay, well, just to be consistent, let's call this now x2. So there we go. I have now a better approximation to the root, x2. Of course, I can continue this process. See, I can continue this process. What I can do here is now take x0 to be x1 and x1 to be the x2. So I have new values now. This is my x0, x1, and this is my x1. My new x1 is x2, and I'm going to find a better approximation, x3, a new red dot. So I have here now x3 is x2 minus f of x2, x1 minus x2 minus x1 over f of x2 minus f of x1. Yeah, I think that's right. And so on and so on. So what we see is we have a recursive process. And for a recursion, you need two things. You need initial conditions and you need a recursion relationship. So we have initial conditions, x0 and x1. They are the things you choose right from the beginning. Here they were chosen as these 2 points. They could be any choice. And we need a relationship, a recursion relationship, so I can deduce that from this. So there it is. This is the secant method. Here are my initial conditions here. Over here, let's use color. And here's my recursion relationship over here. Notice it's a multiple recursion like Fibonacci numbers. It has two previous, the current value xn depends on two previous values, and therefore you need two initial conditions. So that's very interesting. And all right, let's put a big box around this. This is my secant method. So this is very handy to know. And let's make it a bit more specific now. We want to apply it to the case of finding square root of 2. So we will apply this to a concrete example. For our concrete example, we'll take a function f of x is x squared minus 2. So the root of this is when x is square root of 2. And we'll fix one of the initial conditions, the x0, 1. We'll fix it to be 2. And now let's go back and use this recursion formula over here. And we will plug in f of x and plug in x0 into this formula here and get an approximation for x2 from x1. All right. We get this with some straightforward algebra. I plug that into the recursion and I get this. And I can simplify this a little bit. I'll show you. x1 minus there. You can do this algebra as an exercise, and I can do one more step, and I can simplify this a little bit more. We will use these expressions, so I need them. There, very good. So this is x2. This is a better approximation. Let me use some color. This is a better approximation given x1. Now, what I want to do here is drop the 1 and the 2. All right. What I can say is this. Let's say x is my guess, and my improved approximation, my improved guess is 5x. I will apply this function here, the right-hand side, and to x will get closer now, you'll see. So given x, 5x is x minus x1 squared minus 2 over, I should write it like this, x, no 1. I want to get rid of the 1s and 2s like this, plus 2. Or I can also write it like this, 2x plus 2 over x plus 2. All right, so let's think about this because this is an important idea. So what I did here is I got rid of the subscripts, and now I'm saying I take a guess x, and 5x is an improvement on that guess using the secant method. And it's a very simple expression. And the first thing that may come to your mind if you like to read a lot of math books is that this is the expression which is found in Rudin's book. Okay, this book, Principles of Mathematical Analysis. And he does some very beautiful proofs with this expression. And now that we have it from the secant method, we can now follow some of what he's doing in that chapter. But before we do that, let's try some numerical examples. Let's see how well this works. I'm going to choose an x in b, so x is larger than root 2, and let's take x is 3/2. So we'll make a little table. X is 3/2, and this is it's exactly equal to 1.5. But now let's compute phi of x. What is phi of x? That's 10 over 7 if you do the arithmetic, and that is approximately 1.428. So it's getting closer to square root 2, and it's dropping. It's getting smaller. So let's do one more. Phi of x. And what's that? That's 17 over 12, and this is approximately 1.416. So it is getting closer and closer. So for x in b, phi of x is smaller and closer to root 2. Now, that's not a proof. That's just an observation from a numerical study here. We will prove this at the end, but I just want to motivate the idea. I want you to see how it works. Now, another amazing thing about this is that phi works in set A also. So amazingly, the same phi of x expression works the way you imagine it should work in set A, which is probably why Rudin chose this expression. It works perfectly in both sets. Let's see what I mean by this. Let's take an x in set A. Let's take it to be 1. All right, so let's try that. X is 1. And of course, that's numerically 1.0. And now let's compute phi of x. What's that? That is 4/3. This is approximately 1.333 and so on. And now compute phi of x, another approximation. And this is 7/5, which is 1.4. So you see, it's getting bigger and closer to root 2. That's really nice. So let's write that down. So what we see from the data. So in set A, the sequence x, 5x, 5x, so on, approaches root 2 from below. And if you start in B, the sequence x, 5x, 5x, and so on, approaches root 2 from above. So it gets smaller. So that's really interesting. And we will prove this phenomenon in the next part. Now we will prove some properties of phi of x. These are the arguments given by Rudin, and they're very, very clever. These were my two expressions for phi, and these expressions, well, we will use both of them. We need both of them, so let me put a nice colored box here. Part A, suppose x is in set big A, then what? Well, we look here and we can see if x is in set A, then x squared minus 2 is negative. And so therefore, phi of x is bigger than x. This is what we saw numerically, that when we begin in set A, the iterations of phi approach root 2 from below, and so they get bigger. Okay, they get bigger. Iterations get bigger. And what happens when x is in B? Well, x squared minus 2 is now greater than 0. So this negative sign here remains, and phi of x is now smaller than my initial guess x. And these iterations, they get smaller. So like we saw numerically, the iterations approach root 2 from above and get smaller and smaller. Very beautiful. All right, continuing with this proof. Let's examine this expression, phi of x all squared minus 2. So with a bit of algebra, I get this. And notice that here I used, let's use color to highlight this. Here I used this second Rudin expression for phi. All right, that was convenient to use, and now I have the form that I want here on the right-hand side. So now let's choose x in A. What happens when x in A? Well, we can see from here, we can see that x squared minus 2 is negative. And so therefore, phi x squared minus 2 is also negative. And so therefore, phi of x must be in A also, because this is how A is defined. If you scroll back up to the beginning, A is defined as being all the x such that x squared minus 2 is less than 0. So let's now choose x is in b. When x is in b, x squared minus 2 is bigger than 0. Again, same phenomenon happens. X squared, phi of x squared minus 2 is now bigger than 0. And so therefore phi of x is in b also. And so when x is in a, all the iterations under phi are also in a. And when x is in b, all the iterations of phi are also in b. And so it doesn't escape and go somewhere else. It stays. So they go in the right direction. The ones in a get bigger and they stay in a. And the ones in b get smaller and they stay in b. It's very, very beautiful phenomenon. And I think it's worth going through all the little algebraic details to make sure it's completely clear. So in the next part, the last part, I'm going to draw some conclusions about this. Some conclusions. Let's draw those sets again. So A is the set of all x, all rational x, such that x squared is less than 2, and B is the set of all x, such that x squared is greater than 2. So B is up here. The first thing that we see is that any element of B is a upper bound of A. So any x over here is an upper bound of set A. So A is bounded from above. Yeah, except that it doesn't have a least upper bound. That's the problem. It doesn't have a least upper bound. We're talking here about rational numbers only. We have not introduced any real numbers. This is just to orient ourselves. Let's pretend we don't know about root 2. We don't have a least upper bound for A. Let's prove this. Okay. First of all, if x is in A, then and x is a least upper bound, let's say, then phi of x is actually greater than x, and phi of x is in A. So there's no way that x can be an upper bound of A, because phi of x is in A, but it's larger than this least upper bound. Okay, so that's not possible. All right, so B, if x is in B, can the least upper bound of A be in B? Well, no, because phi of x now is less than x, and so phi of x would be a better upper bound. Okay, and it's in B also. Okay, phi of x is in B. And so there's no way that the upper bound can be, the least upper bound of A can be in set B. There's no way, because I can always find an upper bound that's smaller than x just by applying phi. So you see how useful phi is here. Phi helps us defeat these possibilities that there is an upper bound and a least upper bound. And now C, square root 2, well, that's not in Q, so it can't be square root 2 either. So what we see from this is that Q has some problems. We can have a bounded set, okay? So X can be bounded from above. It's like a subset of Q, but there's no least upper bound. So this is possible with the rationals, and I think that this really bothered mathematicians. They didn't like having to live this way. So one solution is they start with Q, and then they use some procedure to construct the rational numbers. Usually this is Dedekind cuts, for example. That's one way to do it, and they construct the reals. The reals are. So the reals are constructed from Q, and the reals, they have this, they don't have this problem of having no least upper bound. Whenever you have a bounded set, bounded from above in R, it does have a least upper bound. So it's not like Q, which doesn't necessarily have that. And so you see, from this study of secant method and all that, we got the motivation to understand, what's wrong with Q and why mathematicians feel it's an incomplete number system, and why mathematicians desire to introduce the reals. Beginning with Q, they construct the reals. And so that's a very interesting excursion, I think, thanks to Rudin and the Secant method. And if you like this video, well, click like, comment, subscribe. I must admit this video was pretty hard to make. It took a lot of takes and a lot of thought, so I would appreciate any comments that you have about it. And I think I will do one more video about the nature of numbers, at least for now. And I will see you next time.